Hi, I'm Mohsin Khan and today I'm going to teach Kepler's second law of planetary motion. It is also called law of areas. It simply states that a planet sweep out equal areas in equal intervals of time while revolving around the sun. So let me explain it to you in detail. Let us consider uh, an elliptical orbit of Earth around the sun. So here is an elliptical orbit. And as we know from the first law that sun must be situated at either of the focus of the ellipse. So the sun must be somewhere over here. This is the location of the sun. So this is the sun shining bright and Earth is revolving in this elliptical orbit. Let's say at this instant of time when we are going to observe the Earth was over here at t equal to 0. And if I draw the position vector of Earth with respect to Sun, it will be looking like this. So this is the position vector of Earth around the Sun. Let us analyze the motion of Earth around the Sun. Right now the Earth is over here, and as the time passes, the Earth will revolve in this elliptical orbit around the Sun. Okay, so simply speaking, its position will change with respect to time, and its position vector with respect to Sun will also change with time. And as we can see that if the location of Earth changes, position vector changes, and then it sweep an area between these two locations. So let me draw the another location. Let's say time elapsed be dt. So after dt interval of time, the location of Earth has changed from this point to, let's say, this point. So here is the second location of Earth after time dt. Now we are assuming that for this short interval of time, this is a short interval of time, speed of Earth remained constant. So let's say that speed be v. The speed is v. And now the location of Earth's new position vector would be somewhere here. This is new position vector of Earth. Let me call this r prime. If I want to write the area swept by this position vector between these two intervals t and dt, I can say that this must be the area. Let's say this area I am calling it dA. So this area is dA. I am separately drawing it. So here is r vector, and there is another vector, a short vector. That short vector can be written as v vector dt. It's simple. The length of the vector is equal to speed times velocity. Oh, sorry, speed times time. So this is the magnitude of the shorter vector. In order to write this area, I can simply vector product these two vectors. So here is, let's say, a vector, let's say p, and this vector be q. In order to write area enclosed by these two vectors, I can simply write dA equal to 1 by 2 q cross p. Right? It's very simple concept from vectors, fundamentals of vectors. So dA is half q cross p. Here q we can replace it by r vector, and p can be replaced by v dt upon 2. This is half of the area of the parallelogram which we studied in vector class. A cross b by 2 is area of the triangle. Right? Now what if I divide this dA vector with dt? So divide dA vector by dt. What do I get? It is dA vector by dt equals to r cross v vector upon 2. Right? Now I am going to make it even simpler. Let me multiply mass and divide by mass. This dA by dt would look something like this. dA by dt equals to r cross. Now I am clumping mass and velocity together so that it becomes linear momentum. So it is mv vector divided by 2m. So far so good. dA by dt can be written as dA by dt is equal to, now this is r cross m times v is linear momentum. So it is r cross p times 2m. If I ask you this, what is this r cross p? We can simply say it is nothing but the angular momentum. Okay, so this dA vector by dt becomes L vector upon 2m. This is angular momentum and relation between dA by dt. But what is dA by dt? dA by dt is called aerial velocity. It is called aerial velocity, or it is the rate at which a area has been swept out by the position vector of planet in time dt, or dA area. I must be saying that it is the dA area vector has been swept out by the position vector of the planet about the sun in time dt. And according to Kepler's law, second law, this dA by dt is constant. But how did he arrive at that conclusion? How did he say that angular momentum, how did he say that aerial velocity of the planet about the sun is constant? Because we know that dA by dt is equal to L vector by 2m. In order for this dA by dt equals to constant, we have to prove that angular momentum of the planet about the sun remains constant. Right? So our new task here is to prove that angular momentum of the planet about the sun remains constant. Okay, so we have already derived a relation that dA vector by dt is equal to L vector by 2m. Here L is angular momentum of the planet. It is angular momentum of the planet. And if we really want to know that why angular velocity of the planet about the sun is constant, then we have to look for the angular momentum. If we could prove anyhow that angular momentum of the planet about the sun is constant, then we can confidently say that angular aerial velocity of the planet about the sun must remain constant. Now, what fact deduces that angular momentum is constant? We have studied that in rotational motion, and that concept is when torque on the system of particle or system of rigid body, or in general any rigid body, is 0, then we can say that angular momentum of the body about any point remains constant. So this is the determining factor. Right, we have to write the torque of the force, and the force over here is nothing but the gravitational force. So if we could prove that torque due to force of gravity on the planet about the sun is 0, then we can confidently say that angular momentum will remain constant. Right, so let's see whether the torque is 0 or not. So here is the sun, and here is Earth, and this with the position vector. Now if I ask you what is the direction of force, Obviously it must be towards the center of the sun. The force acting on earth with respect from sun is must be in this direction, right? And this is the position vector r vector. Now if I write the torque's formula is simple, r cross f. Or if I write magnitude of torque, it is simple, r f into sine of theta, where theta is the angle between r vector and f vector. Here we can surely say that angle between these two vectors r and f must be 180 because they are anti-parallel to one another. Right, so I can say that theta is 180 degrees. So tau of this force or torque of this gravitational force about the sun comes out to be 0. Hence we can say that angular momentum is constant. Since the angular momentum of the planet is constant, now we are confident enough to say that aerial velocity of the planet about the sun must remain constant. So we can in short say that aerial velocity of planet about the sun is constant as a consequence of conservation of angular momentum. Let us also talk about the linear acceleration as well as the angular acceleration of the planet about the sun. At this moment, the force acting on the planet is directed towards the center of the sun. So the force must be acting in this way. And we know that force is equal to mass times acceleration. So acceleration must be force upon mass. And from here we can clearly deduce that whatever is the direction of force at that instant of time must be the direction of acceleration. Now what about the torque? Or what about the angular acceleration? Simply we can write tau equal to I alpha, and since the tau is 0, alpha is 0. Really? If alpha is 0, that makes sure that angular velocity of the planet about the sun is constant. But is it the case? If I want to write the angular velocity at any instant of time, I can say that omega is equal to v by r. Here v is changing, r is changing, and omega is also changing. So omega is not constant in time, it is continuously changing. But we have proved that alpha is 0. So how do you reconcile the fact that alpha is 0 but omega is changing? That is obviously that is not digestible. Alpha is cause of change in angular velocity. Here we have proved that alpha is 0 but angular velocity is changing. There must be some error, and the error is obviously here. We have directly used the formula tau equal to I alpha. That is the biggest error. Tau equal to I alpha is valid only when I, moment of inertia, is constant. And do you think the moment of inertia of planet about the sun is constant in this case? Not the case. See, at this instant of time planet is over here. After some interval of time it will move here. Position vector of the planet about the sun is continuously changing. Hence the moment of inertia. Therefore, we cannot use tau equal to I alpha here. This is the catch. This is the error. And this is the point where most of the students get trapped. So how do we solve that? How do we find alpha? And how do we fix the error we have made? Let's start with that. We'll go with the basic. Tau or torque of a force is equal to d by dt of angular momentum. Angular momentum. Right? This is the fundamental formula. From here we derive that tau equal to I alpha for this special case when I is constant. But here I is continuously changing, therefore we have to go to the basic. Now, d by dt of this L where L can be written as I times omega and I can be written as mr square times omega, where m is the mass of the planet and r is the position vector of the planet about the sun. And we have already proved in the previous case that torque of the force about the sun is 0. So we can say that d by dt of mr square omega must be 0. And here m is the mass, we can send it to 0. And we are left with the term d by dt r square omega equal to 0. Okay, it's just differentiation of two functions. We can use product rule. So we can say that it is differentiation of a second function, which is d omega, keeping the first function constant, that is r square, and then keeping the second function constant and differentiating the first one. It is 2r square, or I must say 2r dr by dt. 2r dr by dt, and that must be equal to 0. Okay, here I am rewriting this equation. It becomes d omega by dt equals to minus 2 omega by r times dr by dt. Here we got r alpha. See where d omega by dt is nothing but angular acceleration alpha. So I am writing it over here. Alpha is equal to minus 2 omega by r dr by dt. Now everything is consistent. We are having a variable angular acceleration, and that variable angular acceleration is the cause of change in angular velocity. Okay, so we have reduced the expression of alpha. It comes out to be minus 2 omega by r dr by dt. Let's see how this omega changing. How this omega is changing. As we have written that angular momentum L, which is I omega or mvr, just a minute, there is mr cross or r cross p, there is r cross p is a constant. So we can say if I times omega vector is constant, and at some point if we know that I has increased or decreased, then omega would go other way. That means if moment of inertia is increasing, omega would decrease. This would decrease. Now let's try to figure out points at which I must be increasing. I is simply mr square, right? It is just mr square. Mass is constant. This term is constant. But the location of the planet about the sun is continuously changing. Therefore, this r is variable. So if r is farthest, which is this case, this is the maximum separation of planet from the sun. At that point of time, moment of inertia of the planet about the sun must be maximum. And since I is maximum, omega must be minimum. So at that instant of time, omega must be minimum. And on the other way, on the other side, this is the minimum separation of the planet from the sun. And since this is the minimum separation, moment of inertia would be minimum, and at that instant of or that location of planet, omega must be maximum. Now let me make you visualize this concept. Farther the planet from the sun, slower is its angular velocity. Closer the planet with respect to sun, faster its angular velocity. So let me try to make you visualize how the planet is revolving. So planet is slowest at that point and continuously increasing its angular velocity. At this point, the planet is fastest revolving around the sun. So it's fastest and then slowest. So it would something like this: fastest and slowest at this point, getting faster again, fastest, and then getting slower and slowest at that point, and then getting faster again. So I hope you understood. It is revolving like this: fastest, slowest, fastest, slowest, fastest, slowest. Now the point here is, how is he doing that? I mean, from where that energy is coming, and from where does this energy, or from to where this energy goes? When it is slowest at that point, here it is slowest at that point, where is the kinetic energy? And when it becomes fastest at that point, where is that kinetic energy coming from? So let us try to understand the energy aspect of Kepler's law. As far as the energy of the planet about the sun is concerned, the energy of the planet must be constant about the sun. The reason is very simple. Since the gravitational force is a conservative force, gravitational force is a conservative force, therefore total mechanical energy must remain constant. Total mechanical energy must be constant. That means whatever energy it has at any point of time in an elliptical orbit, that energy would remain the same. It would remain constant. Okay, we are going to study two special points. The closest one is called aphelion, and the farthest one is called perihelion. At these 2 points, we have deduced that omega at this point, at the point of maximum separation, at this point omega was the minimum, it was the slowest angular velocity at that point, and here it was fastest. Since the angular velocities are here slow and here it is fast, we can also say that linear velocity must also follow the same pattern. At this point, we must have, or the planet must have, minimum linear velocity, and here at the point of aphelion, planet must have maximum linear velocity, right? And let me write the expression for r minimum and r maximum also. As we know from the first law, that the separation between this farthest point of planet from the sun is given by r max equals to a into 1 plus e, and minimum separation is given by a into 1 minus e. It's simple. We know that from center to the focus, separation is a, and this separation is a. Just a minute. We know that this separation is a, so it is a plus a is the maximum separation, and a minus ae is minimum separation. Easy, right? We also know that angular momentum at aphelion must be equal to angular momentum at perihelion, because the angular momentum is constant. So we can say that m times v at a, or I must say v at minimum separation, that means maximum velocity, v at minimum separation, that is maximum velocity, times r minimum must be equal to m times minimum velocity times r maximum. So from here we get relation between v max and v min. So I'm plugging the value of R max and R min. That is V min A times 1 plus E. Okay, so we get the relation V max is equal to V min times 1 plus E upon 1 minus E. Okay, so this is one relation. Let me call that equation 1. Now we are going to conserve energy since the work done is conservative. So work done by all the forces, or I must say since work done is conservative, so work done in round trip must be 0 and the energy of the planet must remain constant. Okay, so the question we were asking that from where this kinetic energy coming at the aphelion point so that it is having the maximum velocity is from the fact that the energy is conserved. Here potential energy must be minimum potential energy, and here potential energy max must be maximum. Okay, so we got one equation over here. Now we are going to write equation for energy conservation. I am going to write that on different page, so follow me. I have to redraw the diagram. This is the sun, and I am trying to draw ellipse and draw an ellipse. Oh, pretty close. And this is the maximum separation with minimum velocity of the planet, and there is the minimum separation with maximum velocity of the planet. Now I am going to conserve energy between these two special points. Okay, so what is the total mechanical energy at point of aphelion? That is this point, and this is perihelion, so I'm calling it EP. That would be EP. Okay, so far so good. It is A into 1 minus E, and this is A into 1 plus E. Now I'm going to write total mechanical energy at point A. This energy must be kinetic energy of the planet at point A, as well as potential energy of the planet and Earth system, Sun system at that point A, which is separation between these two planets is this. Right, it is just half mv square minus g m1 m2 upon r, where r is the minimum separation at point A. Right. Now at point B also, or P I must say, so at point P I can say the velocity or the kinetic energy is half m vp square minus gm m upon a into 1 plus E. Again simple application, kinetic energy times potential energy. Potential energy is gm1 m2 upon separation at the point of perihelion, which is a into 1 plus. Okay, now we are supposed to solve these two equations. Here va is nothing but the maximum velocity and vp is minimum velocity. So I am going to equate these two expressions because we know that except for gravitation there is no force between sun and earth. There is no there are no dust particles, or there is no drag force which can slow down the motion of earth around the sun. Therefore this is the practical case where total mechanical energy of the earth plus sun system remains constant. Okay, so let me equate these two quantities. It is half m, instead of va I am writing v max square minus gmm upon a into 1 minus E. And for P I am writing half m. Instead of this Vp I am writing this minimum velocity Vmin square minus gmm upon a into 1 plus E. This is our equation, let's say 2. Now, how many equations do we have? We have already made an equation in the last page. Here it is, equation number 1, which is relating Vmax and Vmin. And we have another equation, equation 2, which is also relating Vmax and Vmin. If we simultaneously solve these two equations, which is obviously I'm not able to solve here because of the time constraint, after solving these two equations, we get Vmax and Vmin separately in terms of A, E and masses. Okay, so I'm just writing over here, on solving, on solving equation 1 and equation 2 simultaneously, or by substitution we can say, we get Vmax equals to under root of Gm by A 1 plus E upon 1 minus E. And similarly, we get V minimum equals to under root of Gm by A 1 minus E upon 1 plus E. There is super easy way to remember this. You have to remember Gm by A for both the cases. And for minimum, you just put minus sign here and plus in denominator. And similarly for maximum, you put plus sign in numerator and minus sign in denominator. Just make sure that Vmax is greater than Vmin, obvious, for the very obvious reason. Right? So here we have reached the point where we are able to calculate Vmax and Vminimum of the planet revolving in an elliptical orbit around the sun. What if I put these values of Vmax and Vmin in the original energy equation? What do we get? Let's see. So I am going to put Vmax here to this point Va in this equation. Okay, so I am again going to the next page. Energy at point A or aphelion was half mv max square minus gmm upon A into 1 minus E. It is the minimum separation. I am going to put the value Vmax equals to under root of Gm by A 1 plus E upon 1 minus E. So what do I get? I get energy equal to half m Gm upon A 1 plus E upon 1 minus E minus Gm m upon A into 1 minus E. On solving this equation, I get minus Gm m upon 2A. This is the total mechanical energy at aphelion. In fact, this is the total mechanical energy at any point. It is the total mechanical energy of the planet which is constant. Right? So whether I calculate this energy at aphelion or perihelion or any other point other than these 2 points, then the energy of the system of Earth and Sun must remain constant. And see, it is depending only upon semi-major axis for a particular planet and sun. Okay, it is not depending upon the eccentricity. That is the fact I want to reiterate here. Okay, so EA or total mechanical energy of the planet plus sun system is independent of eccentricity of the planet. For a fixed value of semi-major axis. So that means no matter how flat or rounded the ellipse look, its total mechanical energy will be independent of that eccentricity quantity. So for example, if this is the case with one ellipse, let's say this is ellipse 1, and let me draw another ellipse with the same major axis, let's say with some distorted shape. So this is ellipse. But if these two ellipses having same semi-major axis, then both of these two ellipses would have the same total mechanical energy. Thank you very much.